Right, we should. A lot of people just love the work stuff. We have a buddy who's filmed everything.
Like if you know it's got,
That's what it's
only if you know it's gonna be like what velocity you over, you should be ahead.
You can't always do that. Sometimes it's probably good.
Yeah, but like some teachers.
The gen eds want to do that for everything. All gen eds.
Okay, so far we've kind of been talking about cells under standard conditions. What standard conditions are, if you haven't made the connection yet, is standard conditions are 1 molar concentrated ions in solution. Okay. In this section, we're going to talk about the dependence of cell potential on concentration. Alright, so let's just consider this guy. So I get to use all my fancy colored markers today. Okay? So
Black, I'm not doing
So under standard conditions, our concentrations are 1 molar, and our E cell for this particular situation is 1.36 volts. Right? So the question would be then, what would happen if concentrations of things increased? Okay, so we're going to treat this 2 separate ways. We're going to say what happens if the concentration of that goes up in one situation, then concentration of your products goes up in a different situation. Okay? And the answer to this question actually can go back to our understanding of Le Chatelier's principle. The question is, do you remember how Le Chatelier's principle said what would happen to equilibrium if you change concentrations? Yep, okay, so if I'm talking about increasing the concentration of cesium-4+, it would shift to the right. You're adding a reactant. I'm hoping you can remember this. I know Ryland does. Okay, if you're adding a reactant, it's going to shift away. Okay, we could go back and talk about why, you know, the effect on rates due to the collision theory and all of that stuff. Okay, however, we're just going to stick to which direction it will shift. Okay, so it will shift right, which will increase the cell potential.
Why is it shifting for increase cell potential?
Because going to the right increases my reduction. Right, I'm going this to here.
And so the first number, the cathode number, is larger.
What was that?
And so when you find the cell potential,
The cathode would go up.
It's larger.
Yep.
Okay.
Yep. Okay, and in this situation, okay, what I would do if I were increasing now, I could increase both of those concentrations. Okay, and I would cause it to shift away or shift left. Okay, which would cause a decrease in the cell potential. Okay, for the other reason, you'd be increasing the number that you're subtracting. So what's nice is, even in oxidation reactions, we can use Le Chatelier's principle to help explain how the cell potential is going to increase or decrease depending upon adding or removing concentration. I could do then the opposite, but with removing concentration, correct? Okay, if I were to remove, it would shift toward, I don't know if you remember that. And if you add, you shift away. Okay? So, with this then, I want you guys to answer these two questions. And remember that this little degree symbol means what? Standard conditions, and standard conditions for this particular situation is what? Everything is, you know, 1 molar concentration. Okay? So based on that information, I want you guys to predict if it will shift left, if it will shift right, and then if the cell potential will increase or decrease. Got it? You know, sometimes you just gotta appreciate the little things in life.
That's the heart on the board, it's green on it. Holy.
Okay. So it looks like I am increasing the concentration of aluminum in situation 1. Which way will it shift, and what will be its effect on the cell potential?
Shifts left.
Okay? And what will happen to the cell potential?
It'll be smaller. Less.
Okay? And in the other situation, looks like I am increasing the concentration of a reactant, which will then cause it to shift right and increase cell potential. Okay, this isn't an overly difficult concept, so I'm gonna move on. Concentration cell. Okay? What's unique then is if you can change your cell potential by changing the concentration, they can actually make galvanic cells where they have the exact same ions in both compartments. So what this says is a cell in which both compartments have the same components but different concentrations. So I'm going to draw a little picture here. I'm going to just not show the salt bridge here for drawing purposes. Okay. And we're going to have 2 silver electrodes, and in solution, I'm going to have the exact same silver ions. The difference is I'm going to have different concentration of each of those ions. Now they also have 0.1 molar NO3 minus 1 molar NO3 minus there. That just is stating that this silver that formed the ions there came from silver nitrate. The nitrate isn't going to partake in the redox reaction at all. Okay? So, because I do not have the same concentrations, each of these half reactions do not have the same potential. If they were the same concentrations, you would have the same potential, like for example, it would be 0.8 on one side and 0.8 on the other side, and you would just subtract 0.8 from 0.8, and that would give you no cell potential. You'd be at equilibrium, it would make sense. If you got the same things in both sides, the same concentrations, probably not going to do anything. Okay? So, the next question then is, if I do change the concentration, in which direction will the electrons flow? Will the electrons flow from here over here, or from here over here? Why?
Concentration and the Y, something usually flow from higher to lower concentration.
Okay, that's a good guess. Okay, but it actually is not the answer. Okay, now let me show you why. Okay, the best way to understand and to recognize this is to note that in nature what's going to happen then is the concentrations want to become equal. Okay? So the question is how are we going to get the concentrations to become equal? Well, let's try to figure out, I don't know if I've explained super well what exactly happens. Do you remember that visual in the book where the ions gain electrons and then attach to the electrode, and on the other side it was given electrons, and so the solid metal on the electrode was detaching and becoming an ion? Okay? That's what's happening here. So if I have electrons going this way, okay? I'm not telling you this is the correct way or incorrect way at this point. If I have electrons going this way, okay, electrons would come to the plate, they would be giving electrons to the solid on the plate, causing it to form an ion and dropping into solution. That make sense? Okay? What that would do is, wait a second, I think I did mess that up. Hold on.
The silver makes sense, but where does the NO3 come from?
Hold on a second. Oh, no, I'm just looking at it wrong. Okay. So if I take electrons and I flow it this way, okay, electrons are going to flow into here. It's going to start charging this plate. What that's going to do is going to attract the positive ion here and cause it to attach to the plate, gain that electron, and become solid ion. That would reduce the concentration of this. And the opposite would be true here. Okay? If I took and I stripped an electron away from a solid silver atom, it would become what? If I had a solid silver atom, okay, I took an electron away from it, what would it become? Positively charged. So what would happen was, if I would strip electrons from the solid, it would cause it to become solid ions, Ag+, and cause them to drop off in the solution. So what that would do would be, it would increase the concentration here and decrease the concentration here, and that would be creating even a bigger difference. Okay? So instead what's going to happen is, it's going to shift or move, electrons are going to move in the direction that will cause the concentrations to go towards or become equal. So instead, the electrons are going to go this way. Okay? As electrons go this way, what happens then is the plate here gets charged, okay? The silver ions in solution will start to then attach to the plate, going from Ag plus to Ag solid. So I would be taking ions out of solution and be attaching them to the plate. What would that do to the concentration? Okay, it would make the concentration go down, which is what we want. And over here, if I'm taking electrons away, the silver on the plate, if you remove an electron, it will form Ag plus and drop it off into solution, increasing the concentration here. Yes?
How does balance the concentration of NO3?
Those are inert. They're not going to do
Oh,
anything.
okay.
Okay? The main reason why is because NO3 is super, super soluble in water and it's not going to attach to a silver plate. Okay? So, the way to look at concentration cells, which are, again, same stuff in each compartment, different concentrations, is the electrons will transfer from one location to the other in a way that causes the two concentrations to start to equalize. Okay? So, with that being said, I'm going to give you a cell here. It says look in your book, but don't. I'm just going to write it here. Let's say that both of these plates are iron. And then in solution, I've got 0.01 molar Fe2 plus. And over here, I have 0.1 molar Fe2 plus. So what I want you to determine is direction of electron flow and figure out which of these is the anode and which of them is the cathode. The time.
Well, let's see what lessons of another one.
But they don't feel long when I go over, like when I prepare them. I mean, I guess they
There's a lot of
should.
You should
examples.
come.
I know, maybe I've been giving too many examples.
No, they like different examples.
I mean, I wouldn't have to let you do a problem. I could have just showed you one and then moved on. But I'm showing you one and then having you do an example yourself. You don't need to look in your book.
Figure 18.
This is the figure. I want you to figure out, will electrons go this way or this way?
So the way you figure out the cathode is
Which way the electrons go. Right, if the electrons go that way, this has to be the what? Because that's the side that's getting reduced. So really, once you find the electron direction flow, you'll be able to determine pretty quickly which one's the anode and the cathode.
it just depends on concentration.
What was that?
It only depends on concentration.
Have we got an answer?
Yeah.
Everyone? Which way?
Towards the point 1.
So electron will flow that direction. Here's why. Okay, if you take electrons off of the plate, it will form a positive ion, drop off into solution, increasing that concentration. And if you send electrons to the plate, that's going to take the positive ion, it's going to attach to the plate, gain those electrons, and forming a solid, lowering that concentration. So, if electron flow is this way, which side is the cathode? Right. Good. Good. Getting it. Good. I'm going to go as long as I can right now until the bell rings, and then we'll finish the lesson tomorrow. This will be our last lesson. Okay. There was a good old smile to see the little last lesson.
No nuclear chemistry.
Yeah, I know. God. Actually, I found that I kind of have enjoyed. Like, I don't enjoy the work in preparing for the class, but like, I do. Like, I never was like that when I was your age. I didn't enjoy learning things. But like now, and maybe it's partly because I probably have a better understanding of this than you guys do. And so, like I make connections to things because I have a good understanding of a lot of stuff. That it's fascinating. And to me, it shows how great God is, and I enjoy that. So I suppose maybe it's not as enjoyable for you to read a book. You know, if you're just like, I have no idea what this means or how this connects to this or that. Which really ultimately comes down to, Mr. Kramer, you're a bad teacher and I can't teach you guys. So, anyways, in this situation, I'll just introduce this. Okay? Way back in not way back, I guess, last chapter, chapter 17, we introduced this equation. Okay? And in this equation was really the concentration effects on Gibbs free energy. Okay? Because Q was not at equilibrium necessarily, right? Okay? And what we did then is compared standard state equilibrium to some position that isn't at equilibrium. Right? If this was K, then these two numbers would what? Equal each other. Okay? And what you would end up seeing is this plus this would cancel out, making your change in G 0. Alright? However, then, what we can do is since we know that there's a relationship between our cell potential and Gibbs free energy, we could take and we could plug this in, and that's where we get this equation, which is the Nernst equation. So what I'm doing is plugging in this in for change in G, and then the same equation, but only standard, is how we get both of those. And it's kind of complicated, but what you end up doing is both these have negative NF, and I just divide everything by negative NF to cancel these two out, and that's why you see it here. That makes sense? Okay? And so with this then, we can figure out if the cell potential will increase or decrease, and by how much, based on how we change concentration. Okay? Because where is concentration going to really fall in here? What variable will concentration come from? Or,
Q. On the next moles, yeah.
right? Okay, because Q is going to have your equilibrium expression. Okay, now I want to get you one last thing, especially you guys, since you guys aren't going to be here tomorrow. If we are at 25 degrees Celsius, okay, then this is a simplified version of it. I want you to write this in. This is specifically at 25 degrees Celsius.
Is it not supposed to be over?
Uh-oh. Why did I put log? Yes, it's on. So basically what this is it takes R and the temperature in Celsius and your F, because that's a constant, so it's basically constant, and it engulfs them into one constant, and that's what that is. Okay? So it'll just save you some work. If it's at 25 degrees, you can just use this, which is a modified version of that. Okay, and we'll finish this lesson tomorrow for those of you who are going to be here, and then you at least have the equation you guys need to do. It's a Thursday, so you're
Did you hear?